Hello and welcome back to Calculus 2, Chapter 12 on Parametric Equations and Polar Coordinates. Now 12.1 is only Parametric Equations, and we'll deal with the Polar Coordinates whenever we have the next lecture. So for the Parametric Equations, this is going to be a completely new creature to you because we did not have this type of equations. These are going to be coupled equations, paired equations, where they can come in 3s and 4s and so on. The number of equations equals the number of dimensions you have. When you write y equal mx plus b, for instance, you have a variable x and variable y that's 2 dimensions. Therefore, there will be 2 parametric equations involved. So any equations that contain only x and y, which is technically 100% of equations you learned so far, they will be pairs of equations, one for x, one for y. And then when you move into Calc 3, next semester, you are going to see triplets. So x, y, and z, so your parametric equations will have 3 of them in one shot. So now, what do we have for parametric equation? Let me just give you an example. Say you have x equals 3t minus 1 and y equals t squared plus t minus 4, let's say. This would be known as parametric set of equations. Parametric set of equations. And what you do here is you have one equation for x dimension, one equation for y dimension, and both of them depend on what we call parameter t. So t is called parameter. And you can think of t as, let's say, time. So you are talking about how x progresses in time and how y progresses in time independently from each other, but they are actually connected through that time. So what I can do is I can actually work this polynomial out by plugging in one equation into another and coming up with xy equation eliminating t. So that's called a parametric set, but we can convert to f of x, well, y equal f of x by saying t equals x plus 1 over 3, right? When you solve for t, it's going to be x plus 1 over 3. And now you plug in into y. So y is equal to x plus 1 over 3 squared plus x plus 1 over 3 minus 4. And when you just work this out, as you can see, you will get something that is just based on x and y, which is your good old equations you are used to from the beginning of life, right? So we can start with y equals 1 over 9, because a third squared is 1 over 9. So 1 over 9 times x squared plus 2x plus 1 plus 1/3 x, well, we can just do x plus 3. Sorry, x over 3 plus 1 over 3, and then minus 4. So now you have y equals x squared over 9 plus 2x over 9 plus 1 over 9 plus x over 3 plus 1 over 3 minus 4. Find the common denominator of 9 so that you can add all of the values. So y equals, what do we need? We need to multiply over here by 3 and over here by 9. So I have x squared over 9 plus 2x and 3x is 5x over 9 and then 1, 4, and 36 is, no, 4 minus 36. That's negative 32 over 9. And you see that's already quadratic polynomial. If you want to kick 1 over 9 in front, you can. X squared plus 5x minus 32, right? And there you have it. Cool? Now, you would say, why? Right? We can integrate, we can differentiate, we can take the limit. Why? The power of parametric equations, right? Power of parametric equations is not in dealing with things that you are used to with calculus, because you are used to on calculus of functions. You have integral of f of x, you have derivative of f of x, right? These things help you when you do not have a function. How do you integrate a circle? How do you differentiate a circle? You would say implicit differentiation. Yeah, but generally you don't remember it, right? So this is designed for the cases where you do not have a function. And what parametric equations do is they break your non-function into multiple functions, and then you can deal with them, right? So if you think about circle, x squared plus y squared is equal to 16. This is a circle of radius 4. Circle of radius 4. And you can break this into x equals 4 cosine t, y equals 4 sine t. And this is the same, right? So this is the parametric set. And you have a parametric representation of the equation of the circle as these two equations. They provide the same shape, the same picture. Now we have to specify that this t lives between 0 and 2 pi. So these are the same. Now you might say, prove it, right? Well, what I can do is I can again convert this set into the equation up there by simply solving for t in the top one. So t, let's go with cosine t is equal to x over 4, and then t equals to inverse cosine of x over 4, plug in. So once I plug in, I get y equals 4 sine of inverse cosine of x over 4. Do you remember these problems? Sine of inverse cosine, and you had these in your pre-calc course, and there was no context to them. It was all mathematical flexing. Look, Ma, look what I can do. Woohoo, right? But now you see that you can use this thing, right, to transfer your circles and your ellipses back and forth from these forms. And the way you solve this is you draw a triangle on a side, and you fill it with the cosine information, and then you extract the sine. Cosine is adjacent over hypotenuse, which means that this one over here is going to be 16 minus x squared, because this is where your angle t is. So you use the inside of the cosine, right? Because cosine is adjacent over hypotenuse. So x goes on the adjacent on the bottom and 4 goes on the hypotenuse on top. And then you compute using Pythagorean identity the missing side, which works out to be square root of 16 minus x squared. So now you write your sine, and now you read sine off of this one, and inverse, and sine inverse is the square root of 16 minus x squared, divided by 4. And now sine kills sine, inverse sine, I mean. And you have your y equals 4 times the square root of 16 minus x squared over 4. These two puppies cancel. And your y is equal to the square root of 16 minus x squared. Square both sides, move x squared, and there you go. Square both sides. Y squared is equal to 16 minus x squared. And then add x squared. Come on, stop. Thank you. Add x squared to both sides. And you have your x squared plus y squared equals to 16. Cool, huh?
How can you replace the cosine inverse with sine inverse?
Because it's the same triangle. You can replace it with any of the other 5 trig trig functions, because they're all, trig is the relationship between sides and angles in a triangle. If it's the same triangle, you can swap one function with whatever other one you want, as long as it's the same triangle.
I want to think about that one.
Because I need to cancel sine with the inverse sine.
I understand.
The values are the same.
Why? But like sine and cosine wouldn't have the same values.
They wouldn't have the same values, but they don't have the same argument. That one is x over 4, this one is the square root over 4. So they will have the same value. What you said is 100% correct. But if I am replacing cosine inverse x over 4 with sine inverse x over 4, it's wrong.
Right. Okay. Oh, okay.
But this is not the same because I changed the argument of it.
Okay.
So that's that part. Cool. So now we know that we can. Oh, is the lag. I don't know. I'll try restarting. See if that helps. I can feel the lag. Anyway, so now what I want to do is talk more about parametric equations. So actually, let's first write circle is given by x equals r cosine t, y equals r sine t. Ellipse is given by x equals a cosine t, y equals b sine t. So these are your parametric equations. And in Calc 3, you're just going to add the third line of z, and you're going to have a ball, and you're going to have ellipsoid, which is like a watermelon, right? Either way you cut it, it's an ellipse. It's called ellipsoid. Unless you're in Japan, where they have square watermelons, but for the rest of the world.
They specifically growing to the cubes.
They do that with cats.
What?
Apparently the square watermelons also
Yeah.
taste like crap, but they just.
You can also mold the child's head, too.
That I knew.
It's called Bonsai Kitten. It's a
My
website.
brother
Somebody
has
grows
one.
cats in jars so that they grow into a certain shape and feed them with tubes. It's terrible.
Oh my god.
Yeah, they're way ahead of the curve.
Yeah.
That's not ahead of the curve. That's barbaric.
That's not ahead of the curve. Anyway, on a lighter note,
That's actually the area under the curve.
area under the jar, volume, actually. So what we have here, guys, is this parameter t, which needs to be 0 to 2 pi for circle and ellipse. And this parameter t is considered as like an extra variable, which gives us extra degree of freedom. And what it provides to our problems is what we call orientation. For a circle, some people draw a circle counterclockwise, some people draw a circle clockwise. I don't know which group you belong to. You gotta just, naturally. So some people will go woo, and some people will go woo, right? One way or the other way. Now, if you every time you draw a circle, you draw a terrible circle, try drawing the other way. Maybe you are going against your nature. Like if every circle you draw looks like that, then maybe try drawing it the other way. Maybe it's going to work much better. Anyway, so now goes for handwriting as well. So now what you want to do is think about this parameter t as I said, time flowing forwards. T takes value 0, 1, 2, 3, and everything in between. It's not discrete, it's continuous, right? But it has a flow in terms that it grows as you go, right, forward. Now, if I have my parametric set, let's say 2 cosine t and y equals 2 sine t, we can use the information by setting values for t, and we can see which way it draws the image. And the way it draws the image, we will actually say that it moved clockwise or it moved counterclockwise. So if I have my parametric set over here, I can go and say, all right, let's take a look at the chart of values, and then we're going to graph the chart of values. So my chart of values here, and I'm going to start with, I'll need chart with 2 values because I am assigning t and then I'm calculating x and I'm calculating y. Does that make sense? So t will start at 0. We can do pi over 6, pi over 4, pi over 3, and then pi over 2. And let's have a pi. So those are the values. And now we're just going to use the equations up there to calculate x and y, which become coordinates. So cosine of 0 is 1. So this is 1 times 2 is 2. I plugged in 0 for t. Cosine of 0 is 1. 1 times 2 is 2. When I plug in 0 for t in sine, it becomes 0. And then pi over 6, cosine of pi over 6 is root 3 over 2, times 2 is just root 3. And when I plug in pi over 6 into sine, I get 1/2, and then I get a 1 in there. Pi over 4 is root 2 over 2 when I plug in sine and cosine, so this is going to be root 2. Pi over 3 will be backwards pi over 6, and pi over 2 will be backwards from 0. So when you plug in cosine pi over 2, you get 0. 2 times 0 is 0. And when you plug in pi over 2 in the sine, you get sine to be 1. 2 times 1 is 2 for y. If you plug in pi, cosine of pi is -1, so it's going to be a -2 over here. And sine of pi is 0. That's a big fat 0 right there. Now we'll draw axes, x and y. I will use 2 units as 1. These are our standard x and y axis, nothing special going on. And now I have to just plot these points. The first point that I want to plot is 2, 0. That's on x-axis. So it starts there, and that's my t equals 0 value on the x-axis at 2. The next value is 1 and root 3. Sorry, root 3 and 1. Root 3 is about 1.7 and 1, so the next value is somewhere over here. And that's for t equals pi over 6. The next value is root 2. That's about 1.4 by 1.4. 1.4 by 1.4 should be somewhere over here, and that's t equals pi over 4. The next one is 1 and root 3. 1 and root 3 is going to be somewhere over here for t equals pi over 3. And finally, pi over 2 is right there. And we also calculated t equals pi, which is at -2, 0. Do we see how the progression is moving us counterclockwise? So you are going to start drawing at t equals 0, snake through all of these points. This is terrible.
Just go diagonally down.
And it's just going to go to the other side.
It reoriented itself when you moved the screen.
Mm-hmm. Now it's the cell phone quality picture. That's okay. I just had to draw it because I'm standing. I'm not sitting down, so I have no support for my arm. I had to do this. All right, cool. Now, guys, here is something. Please observe the blue. Right? See the arrows? Those arrows are orientation. So we have a counterclockwise orientation when we draw this function. Not the function, sorry, circle is not a function, it's just equation. Orientation, counterclockwise orientation. Can we make it clockwise? Yep.
So I have a question. You get two values for x and y, negative and positive.
Yeah, but I didn't go through all of them. You would eventually go, if you go through every single one of them, right, all 20 points or whatever, you would get them all lined up, and yes, you would have them. So if you swap sine and cosine, guys, you will get the clockwise orientation. Just a side note. Ellipse works the same way because circle is just a special ellipse. Ellipse is the boss shape, and circle is just a special case of ellipse when the A and B radius are the same. That's the same thing that rectangle and square have, right? Rectangle and square are the same family. Square is a special rectangle because rectangle and square have same features, except square has all sides are the same. Well, now when you look at the circle and ellipse, it's the same relationship, except with the radius, right? Radius for ellipse is A and B for minor and major radius, where radius for the circle is everywhere the same. So if you say A equals B in ellipse, you just get a circle. Cool. Let's take a look at another one of these examples where it's not a function.
So is that the ellipse?
No, this is a clockwise circle because I swapped sine cosine.
No, I'm saying what you drew for the marker.
No, this is a club. Okay. So the next part of the lecture is the x equals y squared. So x equals y squared is not a function because it would graph as a sideways parabola, as we are going to see. Now, we can create a parametric set by starting with saying y equals t, and then in that case x needs to be t squared. So we can create a parametric set x equals t squared, y equals t. So this is the fastest and easiest way to create parametric set of equations when you have some kind of equation. You pick one of the two variables to be parameter t, and then the second one is whatever it must be in order for it to work out. Much harder to achieve, obviously, in Calc 3 for 3 dimensions, but for 2 dimensions is fairly simple. So why did I pick my parameter to be y? Because y was squared. And if I square y, then I get x. So if my y is t, then t squared is just x. So it's a very quick way to come up with this. Now you say, well, you didn't gain anything. You still have a square there. Yes, but I have a function x equals t squared, which I can graph, and I can differentiate and integrate easily and do everything with it. Where over here, no bueno, right? So that's the deal. So now if I have this set, I can create, again, the table of values. T, x, and a y. Pick t from, let's say, -2 to 2. And you can calculate your x and y. So all the x's are squares, so 4, 1, 0, 1, 4. And all the y's are the same as t's, so -2, -1, 0, 1, and 2. And now you can draw the graph of this because you have x, y coordinate points. 4, -2, 1, 2, 3, 4, -2. -1, 1, 0, 0, 1, 1, 2, 4. Remember that you started here. This is your t equals -2. This is your t equals -1. This is your t equals 0. T equals 1. T equals 2. So again, we have the way this is oriented, and that orientation goes this way. On the exam, you will be asked not just to graph this by doing the points and graphing, but also provide the orientation. So you have to keep track which is the point that you drew first for the lowest value of t. Orientation, well, I'm going to put that now in blood. Orientation grows as t grows, or orientation progresses. Orientation moves forward orientation. I'm trying to phrase it.
Orientation move. Big.
Pancakes.
Orientation, direction that you could see.
Orientation is in the increasing t. As t increases, the orientation
Orientation is limited by t.
It's not limited by t. Orientation moves in the direction of t, growing t, increasing t. Orientation moves in the orientation of increasing t.
Orientation can change as t changes.
Orientation moves forward with increasing t. It's important to know it's increasing. It's not just changes, because you can change. Change goes both ways. That's why we have positive and negative change. It's not just change. You have to say it in such a way, or understand it in such a way, that as t grows, whatever way the function graphs is the way the orientation is. So for circle, you can talk about clockwise and counterclockwise. For other functions, you can't really talk about it because it's one way. You can go only one way because we're increasing t's, right, from -2 in this case to +2. Yes.
For circles, if you're only doing points, it goes 0 to 2 pi, right?
Yes.
But if it's not, is it always going to be specified that it's between 0 and 2 pi?
No, because you might want a slice. A pizza slice is from 0 to pi over 4.
Can it be greater than?
Yes. You're never supposed to do it, but you can enter the traffic circle, take 3 turns around, and then take the exit.
Okay, so here's my question. For a circle,
It's a ticket, by the way.
if you start at 0, and then you make your first point after that, you make t like.
You don't have to even start at 0.
If you make it 11 pi over 2.
Okay.
So you're progressing along the circle clockwise, but your point, if you're only going in the direction of connecting those 2 points, is going to be backwards.
No, and that if you depends which way you define it. It will be clearly stated that you went backwards. You cannot have it both ways. So when I draw, that's a very good question. I understand exactly what you're asking because it is a point of confusion. So let me draw the full circle over here, and then I'm going to say that there is a pizza slice between 0 and pi over 4. But then there's the rest of pizza, right? So you get this slice, I get the rest, right? So how much did I get, right? I got 7 pi over 4 of the pizza. So this slice here is defined as 0 to pi over 4, and the rest of the pizza is defined as pi over 4 to 2 pi. Now, what happens if I want, now your question, I mean, is this clear? Okay, your question is this, and correct me if I'm wrong, obviously. Your question is, what if I am here, and this is 7 pi over 4, and this is pi over 4. This is your question.
Not exactly. It's like if we went back to the first example that you did for the circle.
Okay.
And instead of putting in pi over 6 or pi over 4 for t, if you started with 0,
okay,
and put in like
pi over 2,
or if you put in 11 pi over 12.
Okay. Oh, 11 pi over 12 would be right here. And
okay. And then what if your next point you put in? If you go around, you want to be here, right? So 23 pi over 12, or just use you can use 11 pi over 6. What if for your next point you put in 3 pi?
You're always going in an increasing t because the values are increasing. Yeah, you go from
t is increasing, but what if you put in?
But all of the other values in between are assumed. This is not discrete. Now you got to snap off your discrete mode and go into continuous. Well, we're back in continuous now. So if you go from 0 to pi, all other points in between, all the other infinity of the stops that you can make are assumed.
So you're not just connecting the points, you're like actually like filling in the circle as you go in that.
Every single infinite amount of dots, right? Okay. All of them are there. Now the confusion is usually, right, as much as we understand, if I have my first pizza slice, there are 7 pizza slices left over here. So we understand that situation. This is the situation that pops up. And you have a 7 pi over 4 here. So you go, how do I describe this one over here? Right? Because
You're crossing 2 pi.
you are crossing 2 pi, and you know you can't use this because 4 pi over 4 to 7 pi over 4 is this piece, right? Well, the key is to know reference angles and understand that at the same point here you have negative pi over 4. So this is negative pi over 4 less equal than t less equal than pi over 4. And we are going to use this particular idea in our polar coordinates next lecture to describe some of the stuff that we need to. So it will be negative. So reference angles help in this case. And you still have now from negative pi over 4 all the way to positive pi over 4, which is 90 degrees. It's a pi over 2 in between. And the orientation will still be counterclockwise over here because we go from smaller number to larger number. You always for t go from smaller number to larger number. And then on the picture, depending on the function, you might go the opposite way you expected it to go. That's okay. Which is why we have cosine and then sine, right? Cosine with x and sine with y to have what we are used to, which is counterclockwise orientation. But if you need the clockwise, you just swap sine and cosine and you get the clockwise orientation. So that's pretty much it.
So t is always increasing?
T is always increasing. This is why you can think of it as time. There's no going back in time, right? If there is a problem of there is a problem of some sort, right? Then you deal with that problem, but there's no going back in time and fixing that problem or preventing it from happening, which is why it's stupid to dwell on the past. I should have done this. Way too late. There's nothing. You're just wasting time by thinking I should have done this. You can beat yourself up because maybe someone told you not to do it, right? But wasting time, precious time, right, afterwards, saying I should have done this, well, I should have done that, and so on, right? Can't do it. So t always goes forward, and it will reveal which way the arrows go. So you have a circle example, you have that parabola example, which was a sideways parabola, and the rest of the problem is going to be, I think we are technically done. I think we just have one more thing to do because that's parametric equations. You have a set of two equations. You can write them as a parametric set or you can just combine them into a single formula. They are designed to break up your non-functions into multiple functions, and in Calc 3 you'll have 3 of these lines. There will be another one for z. We talked about the orientation. We know how to graph. You pick t's, then you compute your x's and y's using the equations. And finally, they have tangent lines. And for tangent lines, we need a derivative, right? So we are going to define the derivative dy dx in terms of the parameter t. So if I have the derivative dy dx, we can just say dy dt divided by dx dt. So this is what you do. So if we say let x be given by f of t and y be given by some other function g of t, then the derivative of these is simply, and I made a mistake. I was about to tell you don't make this mistake. G prime of t divided by f prime of t. So many face palms, guys, on this one. First of all, this is supposed to be red. I'm not sure why it's not coloring the lead. Let's try one more time. When I press red, it should be red. There we go. And now put it in the blue bubble. So now, what's the derivative of a circle? Let's say you have x equals 4 cosine t, y equals 4 sine t. And you want to find the derivative. Well, what?
Cosine, or it's going to be negative or sine t.
Almost, right? Oh no, that's it. But it's negative.
Yeah.
So dy dx will be the derivative in respect to t of 4 sine t, because your y is the second equation. And you are looking for dy on top. So many face palms on flipping them.
Wait, so why is y on top?
Is dy dx for derivative, right?
Can it be dx over dy?
Yeah, but then it's then it's a reciprocal on the tangent. You're looking for a normal line. You're not going to get tangent line. Tangent line is dy dx. Normal line is dx dy. So you have to make sure that you are using right functions. Derivative of sine, so that's going to be 4 cosine t divided by negative 4 sine t. And before you scream cosecant or anything like that, I mean cotangent, you just plug in. See, 4 cosine t is x, so negative x over y. Four cosine is x, and then 4 sine is y, so just plug them back in, and you have that your derivative dy dx is negative x over y. Which you know from implicit differentiation. Let's go blue. Calc 1, implicit differentiation, so we can check the result. You had to take the derivative in respect to x of x squared plus y squared equals 16. That's your circle. And if you do implicit differentiation, you get 2x plus 2y dy dx equals to 0. Move 2x to the other side, you get 2y dy dx is equal to 2x, and then you divide by 2y, you get, oh, this is a negative 2x, yeah, 2y, and then they cancel, and you get your negative x over y, which is exactly what we had with our parametric. So it's kind of cool, right? You can find tangent lines. You can do technically everything that you learned with these as well. It's just that it looks a little bit weird. And 3 out of 4 chapters of your Calc 3 depend on knowing parametric equations. 3 out of 4. That's almost 75%. It's actually about 65% of the course. 65% of the course will use parametrization in Calc 3. If you don't know it, you're just gone. That's it. So learning and studying this right now, yeah, you have one question on the final, right? But if you're going to Calc 3 and you don't know this, there is no Calc 3. It's very simple, right? So you will have to learn and understand this very well if you're going forward. This and the next 2 lectures as well. Chapter 12 is your Calc 3 prep. Otherwise, it's just going to be the annoying 3 problems on the final. If you're not going to Calc 3. That's it. Bye.